In this video, we are going to discuss double integrals over more general regions. In the previous video, we talked about double integrals over rectangles, and now we're going to more general regions other than rectangles as our domain. We are going to start with two examples. I will add a little more background. We will have two more examples and then two problems for you to try for review. We will start our discussions with two examples. So this first one is fairly straightforward. We have this function. We want to integrate it over t, where t is the triangle. X goes from 0 to 2 pi. So here's my x-axis. I'm going to go from 0 to 2 pi, pi over 2. And then y goes from 0 to x. So we know what y equals 0 looks like. And then y equals x is our 45-degree line here. And in particular, we are going to let y go from 0 to x. So we have this region here that we are integrating. When we integrated over rectangles, the limits of integration were really easy to find. This one isn't terribly difficult to find either, but more and more you'll find that it's very useful to map what the domain looks like. So I've graphed here what the domain looks like so I can better get an idea of what my limits of integration should be. So again, my x value can go from 0 to 2, and then my y value, well, I'm going to kind of look at this. Values of y go from 0 up to y equals x, so 0 up to x. And then I have my function here that I'm integrating. It is worth noting I can swap the order of my integration. I just have to be careful that I have my limits correct. So here, if the outer integral is y, I can look and y goes from 0, and here because this is y equals x, this is y equals pi over 2. Then if I look at x, well, it travels from this line over to pi over 2, and this line happens to be x is equal to y to pi over 2. I feel like once you get your limits of integration, then the rest should be fairly easy. So here, my inner integral, I'm integrating with respect to y, so my x is a constant, so I have 1/2 y squared times my constant, and here I have a constant, so that's just cosine y, and my limits of integration are 0 to x. So I plug in my 0 and x, and I get 1/2 x to the 5th plus x cosine theta x. Here I have my integral of 1/2 x to the 5th, so I'm going to have my x to the 6th, and I need to divide by a factor of 6, so I get x to the 6th 1/12, evaluated at 0 and pi over 2. And then here, actually for a moment I thought, oh, I did the wrong thing. Instead of integrating, I did the product rule, but actually this is correct, because if you take the product rule, take the derivative of this, the derivative of x sine x by the product rule is x cosine x. That's x times the derivative of sine of x, plus sine of x times the derivative of x, and then plus the derivative of cosine x, which is minus sine x. So here we have our integral. We evaluate at 0 pi over 2, and our final answer is here, which I did not simplify. Our next example is a little more complicated and definitely requires a picture. And it's find the volume of the tetrahedron bound by the planes y equals 0. So here you kind of think of this plane here. Z equals 0, so everything forward over here. Z is equal to 0. So we're above the xy plane. And then we have this y minus x plus z equals 1. And that is this plane over here. And how did I get this plane? I got it by plugging in numbers. So the first thing I did is I said, well, where along the y-axis does this solid hit? So I plugged in 0 for x and 0 for z, and I got y equals 1. I wanted to know where it hit on the x-axis, so I plugged in where z is equal to 0 and y is equal to 0, and I got -1. And then I wanted to know where it hit on the z-axis, so I plugged in where x equals 0 and y equals 0, and I got 1. So I had these 3 points, and then I know it's a plane, so the 3 points are enough to define this plane, and it's kind of this tetrahedron. Now to find the volume of the tetrahedron, I can treat this as this plane, my minus x plus y plus z, is going to be my function f. So in other words, if I solve for z, I get 1 minus y plus x. That's my function f that I'm going to integrate over my domain, which is the base of this tetrahedron. Remember, the interpretation of an integration of this surface over a domain, an area domain in the xy plane, you're going to get the volume of this solid figure. Now that I know my function that I'm integrating, I just need to know the limits of my integration in x and y. Using this picture, it's easy to see that x goes from -1 to 0. For y, it's really tempting to say y goes from 0 to 1, but that's not quite true. You can see back here, when x is equal to -1, y stays at 0. It doesn't come out here to a y value of 1. But we can look at the equation of this line down here between x and y. That's the equation down in the xy plane. That's when z is equal to 0. So if we set z equal to 0, we're going to get y is equal to 1 plus x. So where y goes from 0 to this line here. So now we're ready to set up our integral. So x goes from -1 to 0. And then inside, y goes from 0 up to this line here, which is 1 plus x. When you integrate, you should get an answer of 1/6. Now that you've seen two examples and have an idea of how this works, let's back up a little bit and just talk in general so we can solve all types of problems. The first thing we want to do is look at different types of domains. So right now we're looking in the xy plane. This is what we're integrating over. So there are three types of elementary regions. The first is type 1, and that's where y, our variable y, is bound between two functions, which we're going to of x, which we'll call phi1 and phi2. Here we have two examples of type 1 regions. So y is bound between, or for our domain, we're looking at y between this function of x called phi2 and our function of x called phi1. So x goes from a to b, and then y goes from phi1 to phi2. This is another example where x goes from a to b, and y is going to go from phi1 up to phi2. You can see then we would set our integral up as x going from a to b, and y goes from phi1 to phi2, and then whatever you're integrating. One thing you should note, the outer integral should always have numbers, because at the end, after you've done all your integration, when you plug in your final things, you should have numbers. I mean, think about it in terms of volume. If your final answer is going to be volume, it doesn't make sense to have functions plugged in. You want numbers plugged in at the end. Type 2 regions have x bound between two functions of y, phi of 1 and phi of 2. So I have an example, two examples here. So here we have y going between c and d. Again, y goes between c and d. Here is the top value of y, see here. Then x then travels from phi of 1 to phi of 2. And then over here, x travels from phi of 1 to phi of 2, and you get your entire domain. And you can see then when you have your integral set up, you have y going from c to this top point d, and then your x goes from c of 1 to c of 2. And last, you have regions of type 3 that combine type 1 and type 2. So this circle here is of type 3, and we're going to do an example with this later. And for completeness, I should kind of define our integral in terms of the Riemann sums like we had in when we talked about double integrals over a rectangular area domain. So our definition is going to be based on what we did for the rectangular domain. We said if D is an elementary region in the plane, choose a rectangle that contains D. So again, if this is our domain, then we're going to choose some rectangle that basically contains D, something like this. Here we might choose this rectangle here. So we have our function that goes from this d to r1, where f is continuous. So now we're going to define our new, our integral that we're looking for over the set by extending f to a function f star. It's hard to see that star, but there's an f star defined on all of r. R is now that rectangle we drew, defined by f star is equal to f of x. So again, now f star is over the whole rectangle, but we set it equal to 0 if f of x is not in our original domain. But now we can use the same definition for integrals that we did for our rectangle. It's just that now the only values that aren't 0 is just when we're over d. And now we have our formal definition of our integral over our domain d. We look at that as it's equal to the integral over r, our rectangle, with f star. And again, f star is equal to 0 when if x and y are not in our domain, if it's outside, like we have the rectangle here, if all this space over here in the rectangle is equal to 0. So we set that equal to this new f star function, which is the double integral here, and you can also change the order of integration. And here I've just also rewrote the integrals with the phis that I had previously written underneath my types of domains. So these ideas here, along with my first two examples, complete kind of my summary overview of this. So in the next slides, I have a couple of more examples for you, and then I have two problems for you to try for review. So this first problem is to calculate the double integral of y, that's our function, where d is the region bound by x minus y equals 0, and x is equal to y squared minus 2. For this type of problem, generally, you are not given a drawing of the domain. It's something you have to graph out yourself. And it's really important to do that so you can figure out your limits of integration. And if someone actually gives you the drawing, like, consider yourself really lucky. But here we have the first curve we have is basically x equals y, so that's just this line here. And this quadratic equation isn't too bad to graph, but I actually just graphed it by plugging in a few points, like the easy points, like y equals 0, x equals 0. But what ended up happening is eventually I did need to know where the line intersects the quadratic equation. So what I did is I plugged in x equals to y into this equation. In particular, I saw this for y squared is equal to x minus 2. And then plugging in for this equation, so I essentially, x equals y, so I plugged in x squared here, and I get x squared is equal to x minus 2. I have this quadratic equation, and I solve where do these two lines intersect or curves intersect. It's when x is equal to 2 and x is equal to negative 1, and then you can plug in for y, and you get these 2 points here. X is equal to negative 1, and x is equal to 2. And now I'm ready to set up my integral. So I put my y, that's my function I'm integrating, and I decided to integrate with respect to x first and then y. So remember, on the outside, you always have to have numbers. So y is on the outside here, and y goes from over here at negative 1 up to 2. And now x, if I have y going from negative 1 to 2, from 2 all the way up here, sorry, not this point, but up here, then x is going to go from the curve to the line. So again, y is going from negative 1 up to 2, and then x goes from the curve to the line. So here I have that set up. It goes from the curve to the line. And from there, it's just calculations, taking the integral, some algebra, and your answer should be 9/4. This next example is kind of interesting. It concerns D, the annular region between two concentric circles of radii 1 and 2. So here I have my circle of radius 1, here I have my circle of radius 2, and I want to integrate over this shaded area here. And I'm just going to set up my integral for a generic function f of xy. Something I do all the time, just habitually, and I don't know if this is good or bad. I think it's not bad. But often, if I see this symmetry, I integrate just this, I'll just integrate this quarter, the first quadrant, and then I'll multiply my result by 4. So, and if we're doing triple integrals, if you do the first octant, you have to multiply by 8. But anyway, so I'm going to do that here. And if I look at this, my first phi1, that's going to be the equation of my hemisphere. Actually, it's over here. But then my phi2, I'm going to have the equation of my second hemisphere, my circle of radius 4, my circle of radius 1. So the thing that's really tempting to do, but it's wrong, is to set up this equation to say, okay, my x values are going from 1 to 2. Oh, actually, they're going from 0 to 1, so this was wrong for several reasons. But I could say, okay, my x values are going from 0 to 1, and then my y values are going from the inner circle to the outer circle. But that's really not quite true. So I can really see why that's tempting, but it's not quite right. When you go from 0 to 1, that's okay, because you are going from the inner circle to the outer circle. It's this region here that's the problem. When you go from 1 to 2, you know, there's not, the inner circle doesn't even exist over here. And in fact, you are going from the x equals 0, y equals 0, the x-axis, up to the outer circle. So the solution is we really need to break this up. We need to break up the x region going from 0 to 1, and then the x region going from 1 to 2. And so here I have my integral. Again, because I'm only integrating in the first octant, I multiply each by 4, and for some reason I switched these two. So I took the x going from 1 to 2, and y again goes from the x-axis up to the circle, the outer circle. And then here I have my x going from 0 to 1. And as I said, then my y goes from my inner circle to my outer circle. So this is how I set up my integral. However, there's still a problem. Normally at this point I would tell you, now that the integral is set up, you can do the integration and the arithmetic, except that there is a problem. And that's, let's take for example, f of x is equal to 1. So then you would have the 4, the 1, 2, and you here, if f of x is equal to 1, you integrate and you get y, and you plug in 0 and 4 minus x squared, square rooted. So then this is what you integrate with respect to x, but this is not integratable. If f of x were equal to 2x, for example, then we would be in good shape. But it was not 2x. So for some f of x's, this will not work. And we really do want some way of expressing this so it'll work for any f of x. So the solution is to divide up the domain like this. So you have the blue domain, which is symmetric to this blue domain down here, and you have a green domain, which is symmetric to this green domain over here. If you're working really fast, you might be tempted to say that in the blue domain, x goes from -2 to +2, but it doesn't, because +2 is out over here, right? Over here, it goes to where the circle intersects y equals 1. So that's the first thing that we need to do. So we need to find the intersection of y equals 1 in the circle, and that's where x is equal to the square root of 3. So this is square root of 3. Now we can set up D1, our blue domain, which is also equal to D1 prime down here. So our blue domain goes from the negative square root of 3 to the positive square root of 3. And if you wanted, you could multiply by 2 and go from 0 to 3. But I did go from all the way from negative to positive square root of 3. And now my y goes from this line here, which is y equals 1, all the way up to my outer circle. So for D2, There's an easy way of doing this and a hard way of doing this, and I often do it naturally the hard way because I often like to have x as my last variable. So I had to, in order to do this correctly, I had to divide up d2 into 3 regions. And the second thing I had to do is I only looked at the top half above y equals 0. So that's 1/2 of d2, but you can see by symmetry the bottom half is the same. So if you wanted d2, you just multiply by 2. And the sections that I divided it up into were based on x equals 1. And then over here at x equals square root of 3. Remember, that's the intersection of the y equals 1 line and the outer circle. And I'll show you why I had to do this division. So I'll start by going from x equals 0 to 1, this interval here. In this interval, y goes from the inner circle up to y equals 1. So here are my limits on y. It goes from the inner circle with radius 1 up to 1. Whereas in this interval, where x goes from 1 to square root of 3, y goes from 0 all the way up to 1. There's no circle in here. It's just the rectangle. So here it's the limits for x goes to 1 to square root of 3, y goes from 0 to 1. And this last interval now, then that goes from x equals square root of 3 up to 2, the edge of the circle. And now y goes from 0 all the way up to the outer circle. So from 0 up to the circle of radius 4, which is square root of 2 minus x squared. So these 3 integrals added together gives me 1/2 of d. And then if I wanted all of d, I'd have to multiply by 2. And if I wanted to integrate with respect to this other d as well, I'd have to multiply by 4. An alternative way of looking at d2, you might have seen this as an elementary region of type 2. So you might have tried to look at the limits of y, in which case y goes from -1 to 1, and x then goes from the inner circle to the outer circle. So that's a perfectly fine way of doing that as well. So this annular region domain deserves some attention when it comes up in problems. There are many little things, if you're rushing through, you might miss. Next, I have 2 problems for you to try. Actually, problem number 2 is actually the easier problem. So if you want to start with the easier problem, start with problem number 2. So pause the video, give the problems a try, and then on the next slide, I will have answers for you. Here are the solutions, and again, you might have done your integral, switching the order of integration, and that's fine, but hopefully your answers at the end are the same. And that's it for this video. Thank you for watching.